Okay, I had a request for a video on game theory. So what you need to understand about game theory really is essentially what's a Nash equilibrium and how to interpret a matrix. So as far as game theory is concerned, the point about it is that when we think about game theory, your key concept in game theory is the idea of what's called interdependence. So hence we see we see game theory generally assessed in oligopoly, but you can see it in any situation where there are two players whose decisions depend on one another. The classic one in oligopoly is should I cut my price? Whether I should cut my price depends on whether you cut your price, but whether you cut your price depends on whether I cut my price. That's what interdependence means. And the way game theory works is it builds a grid that allows us to understand what are the different outcomes for the two different players, and as a result, what their best options are. So the way the grid always works is that we have player one on the left and player two up at the top. We then have two options. It doesn't really matter. Let's suppose we do the pricing thing that we talked about. So player one could play high or low. Player two could play high or low. The first numbers in this matrix are always player one's numbers. I'll make those whatever colour this is, purple or blue or whatever. So if they both play high, let's suppose that player one gets 50. If player one was to play low and player two stayed high, probably player one would win. So let's give player one a higher number like 80. If player one was high when player two was low, then player one would at this stage be doing very badly. They'd be being undercut, and we can kind of say maybe they only end up with 10, as a result of which player one would have to respond. So if player two played low, player one would probably have to go low and would do a bit better than they would if they were still high. So the left-hand numbers are player one's numbers, and let's suppose that those are profits in some sense. Player two's numbers, we'll put those, they're always the second number in the grid. So let's suppose that if they both play high, let's suppose that player two is slightly less efficient. So they both play high, and player two gets 45. This box would be player one plays high, player two plays low. Player two is going to do well out of that. We'll give them a number like 65. If player two is playing high and player one is playing low, player one is now undercutting player two, so player two is probably toast. And finally, if they both play low, then let's call that again we'll call that 20 for the sake of argument. So those are the profitability figures. Sorry, that's not very clear, that one, is it? That was 45. So those are the profitability figures. So when we're trying to work out the grid, what we do is we simply say, well, what is the right thing for player one to do given what player two does? So what you do is you take one player's decision and you simply say, what if player one did this? What would player two do? So let's do that. So if player one goes high, that's there, we simply say, what would player two do? And all we do is we look at the two player two numbers. 65 is more than 45, therefore player two would play low. And we can double underline that to show that that's the thing that they would do. Now we simply go, if player one played low, so there, sorry, we said that player two would play low. If player one played low, what would player two do? So we go, right, okay, player one is playing low, player two has the choice of either 20 or 15, so player two would go low again. We now reverse it, and we simply say, if player two played high, which is there, what would player one do? Now, player one's numbers are the two purple numbers. Player one would play low. And finally, if player two was to play low, what would player one do? So we go, player two's low, player one's are the two purple numbers. So they'd rather have 20 than 10, so they would play low. And we can underline that. If you get two underlinings in the same box, that is going to be the outcome. That is a stable situation. That is what's called the Nash equilibrium that I'll come to in a minute. So if you get two sets of underlining in one boxes, that's where we're going to end up. So hence low, low in this case. So what is this Nash equilibrium? That's the other thing that you need to understand about game theory. So a Nash equilibrium is in simple terms, the way I've kind of done it in an informal way. A Nash equilibrium is you move, you lose. And that's probably the best way of thinking about it, yeah? If you change your strategy, you lose. The proper definition, yeah, it's a situation in which no player can gain by changing their strategy alone. So if you're the only one to change your strategy, you would lose. So if we reproduce the thing that I just rubbed out a minute ago, so we had player 1 and player 2, high, low, high, low. I can't quite remember the numbers anymore, but that was something like 75 and 6. No, wasn't God, it doesn't really matter. We'll call that 120. We'll call that one 20 and 90. And that one can be 30 and 30. Okay, so let's go through the process again. If player 1 plays high, then player 2 would play low. If player 1 plays low, player 2 would play low. If player 2 plays high, player 1 would play low. And if player 1 plays low, so player 2 plays low, player 1 would play low. So we're saying that is the Nash equilibrium. But what we need to understand is, what is it about that? Can we prove that is the Nash equilibrium? And the answer is, well, yes, we can. And the way we do that is we simply say, well, what happens if somebody changes? So let's suppose, so at the moment we're in a low-low situation. Suppose if player 1 suddenly goes high. Let's see what would happen to them. That's player 1's number, which is 30. Let's see what would happen if they went high. Their high is there, they go from 30 to 20. So if player 1 went high, they go from 30 to 20, so therefore they wouldn't want to do that. Let's now look what happens if player 2 suddenly decides that they want to go high. So currently player 2 has 30. If they suddenly go high, so there's the player 2 strategies there, then again they go from 30 to 20, so they wouldn't want to do that. And therefore that's the Nash equilibrium. Neither of the players wants to change by themselves, and that's what a Nash equilibrium is. In terms of what this, what other things you can do with games. So that's the key for what you need to know. In terms of other things that you can, that it's worth thinking about in terms of game theory, we can see that in reality this is a shit outcome. They're both ending up with a very low level of profit. Whereas if they were able both to play high, then they'd both end up with more profit. So hence, what you can use this game theory for is you can show that that's the reason that firms might want to collude. So they might want to choose to come to an agreement. Or possibly one of the players could deliberately sacrifice themselves. Perhaps player A, who does better out of the deal, perhaps player 1 rather, who does better out of the deal, perhaps player 1 could decide that they're going to sacrifice themselves and play high, sending a signal to player 2, hoping that player 2 will respond. But what we can see is that this grid shows the clear motivation for firms to collude. If they collude, they end up with 70-65. If they engage in a price war, they end up with 30-30. Therefore, the other thing you can use game theory for is to show that there is an incentive to collude. And just very last thing is the Nash equilibrium also shows that often in oligopoly we will have price stability. Nobody particularly wants to change their price. So therefore again, you'll get periods where prices are relatively stable, but not necessarily, inevitably, not forever. It's possible that a deal will be struck, and they'll end up with high. But of course, once we're both high, there's always an incentive to cheat on the deal. So oligopoly is a complicated market structure. But in terms of what you need to understand here, can you interpret a matrix? Can you find the Nash equilibrium? If you can do that, that's the key.